Okay, so I think we should continue. We will stick with a similar subject, the mathematics of surfaces. It's my pleasure to introduce our next speaker, Bjorn Stinner, who actually earned his PhD in mathematics from Regensburg and then moved to Britain. Now he's an associate professor at Warwick. He will talk about surface finite element methods. The floor is yours.
Yes. Thank you very much for the introduction. And also thanks to the organizers for inviting me to make a contribution here. So I've added a subtitle. Yes, I want to talk about methodology, but I want to also consider a specific mathematical problem. And namely a problem where we have a geometric partial differential equation that describes the evolution of some curve or some surface. And we want to consider some lateral process, some diffusion process typically, which takes place on that surface and then backcouples usually to the geometric evolution. Yeah, and then later on, to give you a short outline, so we'll introduce you a bit to the variation formulation and how that method in principle works. I mean, we have seen a bit already about moving mesh, what the typical difficulties are, but actually in some cases one can get hard convergence results for this method. Yeah, I want to present one of these results. And then in the second part of my talk, I want to talk about some applications. I don't want to go into the details of the convergence proof, but rather talk about some applications. So we have used such type of reduced models to model cell motility, and even did some quantification of cell growth with image data. There is some preliminary work on focal adhesions, and time permitting, I will towards the end then talk a bit about tethering, how that might be useful. It's just an idea, essentially. Yeah. Okay, so what's the problem like that I want to talk about? So I said we have a geometric equation. So we've got a moving surface or a curve denoted by gamma of d, and we have some quantity c of d on that moving surface. So first, the surface is evolving. A priori we don't know what it is. We have to compute it. So it's given indirectly by a geometric PDE, which could look like this in the simplest case. Yeah, so we have here a term which involves a normal velocity, omega as a positive coefficient. Yeah, we might have some curvature term here coming with a surface tangent, and usually there will be a coupling term to the surface quantity itself. And it might be, depending on the application, it might be possible to derive such a system from physical principles. So there might be a viscous environment which opposes the motion of the surface. There might be some mechanical effects later on. Yeah, this is just a surface tension, and in that case, we are going to look at higher order equations later on as well. Yeah, and the coupling effects, you might interpret this also as a forcing term, yeah, which arises from this quantity on the surface itself. Yeah. Good. So how about the surface PDE? So it's subject to such a reaction diffusion equation as stated here. So we follow trajectories of material points. So here in this case we have motion in the normal direction, so material points move in the normal direction, and this is then the normal time derivative, or here it coincides with the material derivative if we follow these trajectories. Yes, we look at the quantity on such a material point and look at what is the time derivative along these, if we follow this trajectory. So now if you have a curved surface or a curve, which actually is curved, not just planar, then if you move it in the normal direction, then it's going to be stretched or compressed locally. And this term is accounting for that. So if the C here really is a conserved quantity, as I'm writing it down here, modulo the reactions, I should say, if it's really conserved, then you will obtain such a term which accounts for the local stretching and compressing. Furthermore, in general, we will want to account for some diffusion term, the Laplace-Beltrami operator features. Yeah, and we might also want to account for some reaction terms written down here as an abstract function R of C.
Does the stretching, I'm not sure what the negative sign means. Maybe
it comes from the curvature. It depends on how you define the curvature, which it's a scalar curvature here. Yeah.
Right. So should I link this to dilution or because you're stretching the surface or concentration?
Well, roughly speaking, these are positive coefficients, the Ks and the omega. So in the simplest case, the normal velocity equals the curvature without the coupling term. So this gives a quadratic term, yeah? So if you put it to the other side, yeah, so it's just the right sign that you want, yeah? Okay. So Just to give an example, what you then expect to get. So you've got a geometric evolution of the surface and some process on the surface, which could look like this. Yeah, in this case, it's describing some phase separation on the surface. Yeah, but it's a coupled process. The surface is evolving, and there's a process on that surface, given by this such a parabolic type of partial differential equation. Okay, so how can we discretize that? So I have been using surface finite elements to do so. So we're going to approximate the curve of the surface. Here it's about the surface. For a curve it's going to be simpler. It's just a polygon. Here for a surface we are going to use a polyhedral surface consisting of triangles. So we're going to approximate the gamma of t by gamma h of t, a collection of triangles, where this h here stands for the size of the diameter of the triangle. So later on I'm going to talk about sending h to 0, yeah, so that way we want that the approximation of the surface gets better, yeah, and in the end we obtain the gamma h that approximates the gamma. Yeah, so what else do we have? We have some more structure. So these triangles are the images of a reference element under some shape function, and I will consider linear functions and quadratic polynomials for this purpose. But in principle one can use a different type of shape functions as well. But these shape functions are then also used to define a finite dimensional space by which we attempt to approximate quantities on the surface. That's this here, the finite element space. Yeah, so in this case I'm going to consider continuous functions on the whole discrete surface, yeah, which locally on each of these triangles here, modulo mapping back to the reference triangle, yeah, corresponds to this finite dimensional space of shape functions. Yeah, so this is the finite dimensional approximation of this surface field. Right, so now we have a discrete setting. How can we approximate these equations that I've presented before? And I want to focus here on the geometric equation because that's the more tricky case. I find it a bit more tricky. And I want to give you some details on how that works for the mean curvature flow. You know, very simple equation. The normal velocity just equals to the curvature. And I want to report on a method that has been developed by Gertjuk in the end of the 80s already. And then subsequently these ideas in that method have been used to set up several other types of schemes. So there are two essential ideas involved. The first idea is, okay, we're going to write it as a vector valued equation. So the vector valued velocity equals to the mean curvature vector. And then for that to represent the curvature vector, we shall use the identity map denoted by x of the surface. It's just taking a point on gamma and mapping it to itself. But it's a map now. Because it's a map, you can apply the Laplace-Beltrami operator to it. That's the right setting. That's why I don't need a map. Yeah, but you can think of x being just the coordinates of the surface if you want so. Yeah, but you can express the curvature vector, the mean curvature vector like that, with a Laplace-Beltrami operator. And then testing, multiplying with a test function, integrating, and then applying some surface calculus, you can come up with this integral here, representing this right-hand side here. Yeah, so you see, only first derivatives feature in this context, and we are integrating up. So this is a nice variation of formulation for the mean curvature vector. And this is accessible to these finite elements that I've introduced before, because we only have first derivatives now, and integrate up. This is a nice variation of formulation. Well, and here on the left-hand side we have kind of the time derivative of the coordinates, so that represents the velocity. Yeah, so this is a variation of formulation of the above geometric evolution law. But of course it might look like a weak formulation of the heat equation, but of course it's highly nonlinear. Because this x here is coupled to the gamma, the identity of gamma. It's highly nonlinear. Right, so then there's a second idea involved. How can we discretize that? Okay, in space it's rather straightforward. That's what mathematicians and numerical analysts do. Just add an h everywhere and it's discrete, yeah, at least in space. So, but then there's also the time discretization that you have to do. So I introduce some time steps. And then the second essential idea is to get a consistent approximation of this equation and to get a nice linear system. So you approximate the surface for the next step on the actual surface, on the current surface. Yeah, so in mathematical terms, Yes, if you have your polygon, a polyhedral surface, you compute the surface for the next step on the actual surface, which means that you integrate on the actual surface and you carry out all these surface gradients on the actual surface. Yeah, that's the essential idea. Yeah, so in mathematical terms, you compute a finite element function which satisfies this equation. So towards the time step here, you recognize a discrete time derivative. Yeah, and here, with regards to this curvature term, you see we carry out all the calculations, the surface gradient, and also the integration of the actual surface, and then compute this field y, which serves to define the surface at the next time step, which is obtained just as the image of the actual surface under this map y. Now that's the second essential idea. And it's important to have consistent approximation. So this here it's a consistent approximation to the second order operator. Curvatures are associated with second derivatives. So to get a consistent approximation with, say, linear finite elements, for instance, it's not that straightforward, but it works thanks to this time splitting, thanks to this time discretization. Okay, so we can use these ideas then also to set up other schemes and even approximate higher order schemes. So here's an idea, for instance, for the Wilmer flow. The scheme stems from Bergak and Nuremberg. So they keep the kappa to some second order operator splitting, again to be able to use, for instance, linear finite elements. So looks like that. So here again is the time derivative, and then here you have kind of a weak formulation of the buff right hand side involved there. And then I said you keep the kappa, and this is basically the equation that we've seen before for the mean curvature vector, which is here the second equation. That's the second equation. And then you can discretize that with the means I've presented before and compute solutions to the Wilmer flow, approximate solutions to the Wilmer flow. Yes, maybe I should mention that there's a second fundamental form involved here, which is a bit difficult to approximate if one just uses linear finite elements. So Bergak and Nuremberg came up with a method to do so, but they couldn't prove convergence. If you use higher order finite elements, then it's definitely in a safe setting. So using quadratic finite elements definitely is sufficient to get a consistent approximation of that operator. But they did it also for linears, and in practice it still works. Okay. So that much on the geometric equation. Now, what in general happens if you move meshes, if you move vertices, of course they can degenerate. So some of these schemes that have been developed in the past, for instance here the Bergak and Nuremberg scheme, but also here the Charlie mentioned on Monday, I think the new scheme that he has developed with Hans Fritz, they showed in general a good mesh behavior because there's some intrinsic there's some tangential motion of the vertices involved. Recall the geometric equation means everything is moving in the normal direction, but this is typically coupled now to some tangential motion of the vertices, and then this is beneficial for the mesh quality. Nevertheless, I worked quite a lot with this Bergak and Nuremberg scheme, but often enough, when accounting for additional effects, sometimes that turned out to be insufficient, and occasionally I had to resort to some other external remeshing methods. So I usually used that one. There are several remeshing methods around, of course. I used here this method. I hope it's still available. I didn't double check that link. A remeshing method developed by Clarence and Juk. He gave once a talk here at the Newton Institute about that method. I think it's never been published. There might be a preprint though. And to give you an idea of how that remeshing method works, let's look at this example here. You can see here these small, very thin triangles which don't have a good shape. So if you then apply the remeshing method, you obtain something like that. Let's go back again. When you see here in this necking region, you get much nicer triangles. Afterwards you might say, okay, I'm still not quite happy with that mesh, so these triangles here are far too fine, whilst here I have quite coarse triangles. So usually one also has to apply some adaptivity to adaptively refine or coarsen the mesh afterwards again. And I've usually been using some just ad hoc methods which are based on the surface fields. So whenever you have strong gradients of your surface fields, you should refine your mesh there. But of course, they also have the geometric equation, and you should use here areas where you have a high curvature. Those should also be refined a bit. Just not hoc method, yeah. So going back from here, we might do some adaptive refinement and end up somewhere there, yeah. Somewhat smaller triangles here and somewhat coarser triangles there in the neck. And then you might go on with your computation of the flow, yeah. Of course, for an analysis, this is difficult to handle. In principle, what could happen is that after each time step, you have to do some remeshing. Yeah, so that makes the analysis of surface finite element methods for geometric equations, for geometric PDEs, quite hard. Yeah? But actually, in one spatial dimension, it can show something. The surface PDE. I almost forgot about that one. I've been using the method by Jook and Elliott to do so. So it's based on this weak and variational formulation for the surface PDE that I've presented before. The discretization, and it's rather straightforward. Again, add an H to all the quantities for the spatial discretization and do something about the time stepping. Then here, there's a time derivative here. Might just do something like that with a backward Euler to get it stable. Well, stable, there might be an issue with the reaction terms, of course. You have to deal with them as appropriate. Yeah.
As a non-expert.
Yeah.
So I see all these integrals. Do I understand correctly that you then put in shape functions and turn this into some algebraic equations in the end?
Yeah, in the end, yeah. Yep. At some point you're going to linearize, be it here in the scheme already, or if you take that implicitly, if you have a nonlinear equation.
I think you
So with a Newton linearize there.
I'm
Yeah.
also assuming that you have already computed the surface, because it's important.
That is true, yeah, that's
Very
true.
important.
Here's the next surface already. So what I usually do for the coupled systems, I first compute using the old fields, I compute the new surface using a geometric equation, and then afterwards I update the surface field, the C, on the new surface. Yeah. Good. Okay. I think Charlie talked about that on Monday, at least to some extent. Yeah. And at least he mentioned some results, how this method here, on the analysis of this method, for in the case that the evolution of the surface is given, one can do that. Yeah. As I said, in this case, if the surface is unknown but implicitly given by this geometric equation, this is much harder. But we have some result, and this is a joint work, a recent work together with Paola Pozzi. So we work in a parametric setting. We parameterize, actually it works in 1D only, so we have a curve, an evolving curve. We parameterize it over the unit circle. Yeah, the geometric equation for this curvature flow then reads like that. And this f of c is the coupling term again. Yeah, and you can also rewrite the surface PDE in the setting here, which then reads like that. Yeah, so that's the system. The difficulty mainly then comes here from this length element. Yeah, so this is what makes this equation highly nonlinear. So you have to control the length element, the ux. Yeah? Right, so in the discrete setting, this is basically translating what we've done before and to this parametric setting. So I'm integrating now over S1, but you can write this also here as an integral over gamma h, just coincides one-to-one. There's some interpolation involved here, this IH, but apart from that, it's a rather straightforward way to spatially discretize the above system, the variational formulation of the above system. And I should also mention we are using linear finite elements here. Yeah? So we are searching for functions u, which at each time are these are vector Wellert linear functions, and c is a scalar linear function, piecewise linear function. So what we also need is a nice and smooth solution to the underlying problem. So that essentially is an open problem, and you can easily imagine situations where this coupled geometric equation with the surface equation can generate all sorts of complications, self-intersections, or other types of degeneracies. Yeah? So we have to assume that we have a nice and regular solution, in particular a solution such that the length element is bounded from below uniformly. That's very important. Yeah? So this guy here has to be uniformly in time and space bounded from below. But if we have that, Yeah, then we can show that there's a unique solution provided the h is small enough, yeah, provided the edge length is small enough. There's a unique solution to this discrete problem, the semi-discrete problem, I should say. We are still continuous in time, yeah? And we can show these error estimates here, these two error estimates. Yeah, for the error, for instance, here of the unit tangent, for the derivative of the c, etc. Yeah. So, some remarks on the proof, which are mainly targeted at the experts on these types of equations, and we will not go through the details. So, we could, I mean, Gertjoke has looked at the mean curvature flow already and has proved convergence for the curve shortening flow. In particular, he has proved an estimate for this length element to control the length element. Yeah, so we could build up on that. But the essential difficulty, the novelty here, consists in the fact that we here in the equation for c, we've got the time derivative of that length element. So that requires an additional estimate. Yeah, so we've got this term here in the c equation, and we need to estimate this guy here. Yeah, now the key observation was made by Paola. You can write down this term here in terms of other quantities which we can actually control, which we can much better control. Yeah, and thanks to this, if we mimic this calculation, this is a fairly simple calculation here in the analytical setting, but if we mimic this calculation for this difference here, yeah, then we can actually derive an estimate here for the error of c minus, yeah, for the error in the surface quantity. Yeah, so that was the essential extension that we needed to prove this existence, this convergence result here. All right, so I should mention that these estimates are not optimal. You would expect a bit more here for this error here, c minus ch. You would here expect the power 4. We couldn't prove that, but in the convergence test, the numerical convergence test, we definitely see that. So we get the higher order convergence. Yeah. Okay. So now we've got quite a rigorous and a robust setting for these types of problems. Let's see what we can apply it to. And I want to start with the cell motility. And the first example concerns the persistent motion of keratocyte cells. This is joint work with Shekhar Venkataraman and Charlie Elliott. So we found a model proposed in the literature by Shara Pellant-Levin, which involves a phase fit model for the cell domain, for the evolution of the cell domain, and a Turing system within the cell for the actin. In this case, it's, well, let's say for the actin filaments and the myosin essentially. Maybe it's better to think about some quantity that leads to protrusions and some other quantity that leads to retractions in the end. Okay, so, but we observed that this coupling between this Turing system and the phase fit model actually only took place on the boundary of the cell. Yeah, so why not then just formulating this Turing system on the boundary of the cell? Formulate it as a surface PDE, and see whether that works as well. Yeah, so that's the system. A is the quantity responsible for the retraction. There's a coupling term here in the geometric equation, so this Kp1 is negative. Kp2 is positive, and this is the term A2 is then the quantity, the field that is responsible for the protrusion. Right, so that's a geometric equation then, and there's a Lagrange multiplier involved because we wanted to keep the enclosed area preserved for curves only here in this case. Yeah. So there's some results. Essentially that does work. So here's we start with a sphere, geometrically it's a sphere, and then we have a slight perturbation to initiate the evolution in a certain direction. So a slight perturbation which you can't see here. So and then we vary this parameter Kp2, which is responsible for the protrusion, and depending on that parameter, this is always at a specific given time here. We observe for different values of Kp2 these different shapes and these different speeds, so to say. Yeah? So the different distances to the initial position which is here. Yeah? So the higher the Kp2, the further it's going to be away at that time. Yeah, so here we are displaying the A2 concentration, which is high here at the rear of the cell. It's responsible for the retraction, so you would expect that. and it's low at the front, and it's the other way around here for this A2 field. Right, so we can attempt to quantify that at least in a vague way, yeah, compare the shapes a bit with what can be observed, and also the aspect ratios, and also the speed of the cells, and roughly, we are roughly in the right range. Yeah, so maybe you can spot these dots here of our computation here in this field, which has been taken from the literature, this figure here. Right, so that was one example. Another example, so yeah.
The red line was the model by Herbert Levine.
This is not our prediction. This is from that paper, some other prediction.
Yeah, but didn't you implement exactly the same model like?
No, we didn't do what they did. We have a different model. Yeah.
But you could compare with the Levine model.
So which one?
The one by Herbert Levine, the one you cited.
Right. Yeah. All right.
And there you get the same results.
Did we? We have done some comparison with that one as well. Yeah. Not reporting that one here. Yeah.
I don't think they did this parameter range that Bjorn's talked about. I don't think they looked at a range of parameter values. So this comparison you can't do directly with what they did.
Yeah, qualitatively you could compare that. Yeah. I mean, of course, you have a surface equation instead of a bulk equation. It's going to behave differently, yeah. But you can get similar shapes, so as such you can compare it. Yeah.
I'm an experimentalist. I'm asking maybe a stupid question. Would that, so you've calculated this now for a 2D object.
Yeah.
Would it be possible to do it for a cell that is obviously a three-dimensional object?
Yeah, the
And
method
would noise destroy this calculation? Because
noise is delicate. I mean, a ad hoc way would be adding white noise to something, to your mass equation. I mean, if you do that to the C equation is backcoupling to the geometric equation. So you're going to totally destroy your surface. You're going to get a rough surface. You have to be very careful with what type of noise to add. And some smooth type of noise, that might be possible. Make an ultraviolet cutoff. Yeah, that should be possible. So, yeah. That's maybe, well, noise is affecting the diffusion as well, yeah, if you have a rough surface. So this has been analyzed actually by a student recently at Warwick who did that, considered that in a homogenization setting, yeah, computing effective diffusivity if you apply all sorts of noise to your underlying surface. But, yeah, so there are some hard results in that context as well. Yeah, it does play a role. And if the noise is smooth enough, yeah, probably it's possible to do that. There is some noise involved in the second example actually, but that only enters at the discrete level, not at the continuous level. Yeah. So actually we picked up this model, here John talked about these, we showed some very nice simulations on Tuesday. So we picked that up and could confirm some of these results, most of these results, at least those that we have considered. We haven't done all of that again. Yeah, so this was for the protrusions and the retraction. That was a model which goes back to Meinhardt, essential equations. We've slightly changed them. First, this diffusivity for the quantity B is quite high, so we've just replaced the B by the average of A, and in the geometric equation we've added some additional terms. Oops, back, there we go. Yeah, so be it that you want to account for some additional mechanical effects, but you could also just consider that as regularization parameters if you want. So, yeah, add some surface tension, add some bending rigidity. Yeah, but here in this context, the noise only comes in at the discrete level. Yeah, so we discretize in space and then let this S here then back couple to the equation for A, which is responsible for the protrusions. Yeah, so the A is the quantity that couples here to that's involved in the coupling term to the geometric equation. Yeah. So I think I don't show that again. We've seen these simulations. We've also seen these spider plots. I hope you can see that at the rear in particular. So there's this parameter rho here, which is related to the gradient of an external chemoattractant. And the higher this gradient is, the more directed is the motion of the cells, and that can also be compared to some extent, for instance, in terms of the chemotactic index and the persistent length. Yeah, so the higher the row, the higher you get these values, and this is also quantitatively comparable with what you see in the literature. Well, of course, this is also kind of a very macroscopic test, kind of a macroscopic way how you compare with the results in the literature. Nowadays, if you look at the data that you get out, this image data, you can retrieve much more information. You can retrieve information on the geometry. You can retrieve information eventually on the density of certain substances. So the question came up, can we fit parameters to the geometry and the concentrations, to data that are obtained from images? Yeah? So we could start with something like that as an abstract setting. Yeah? Say there are some parameters that we want to identify, diffusivities, reaction rates, whatever. We've got some observations. Yeah? So here in this context, I first assume that the observations are really curves, gamma hat, with some surface quantities. It's denoted by a hat here. Could be a vector valued quantity. Yeah. Yeah, and then by gamma and a, I denote the solutions with the solution which now depends on this these parameters c. Yeah, and now you have to compare that somehow. You have measured the data. You've got your computed solution. In one way, could be like that. Yeah, just compute the distances from the computed surface to the measured surface. Put that into an integral and into the functional here. And similarly, to make it symmetric the other way around, yeah, compute the distance from the measured surface to the computed surface. Yeah, so that way you would fit to the geometry. Yeah, and with regard to the surface quantities, there's this closest point map here involved. Yeah, compute for a given point x on the computed surface, compute the closest point on the measured surface, and the other way around, and compare the values that you have in these points. Yeah, of course, this is hard. This is highly not. This can be quite singular. This is lacking smoothness. Yeah, so we have worked with a smooth version, which is inspired by the phase field methodology, but I won't go into the details of that. I expect that Shekhar in his talk tomorrow is going to pick up on that methodology, how that works in the phase field context. Yes, I'm only going to talk about this setting here, yeah, for which we got some results. Yeah, but it's lacking theory. It's still lacking theory. So the discrete setting. Right. So what do we assume here? So we've got some approximations to our data. Gamma hat h hat, and we've got the computed solutions, gamma h a h, depending on the parameter c again. So then we want to compute the distance, and here we make our life easy by just comparing vertices. So this way, of course, if you compute the distance, you're going to lose one order in h, but we can still live with it. So if you just plug this distance here into a discrete functional, it's still consistent. Yeah, if you can let the h and the h hat converge to 0, you still get an approximation of the continuous functional under suitable assumptions on the curve on the data and on the computed curves, of course. Yeah, so if you're close enough together, then that will work. Yeah.
Do you have a unique minimum?
This already depends on C. What you said what C is, that means said what the model is. No, in general not, of course. Okay. Yeah, you're going to all sorts of problems. In that context as well. So the energy landscape in general will be complicated. Yeah. Yeah. So tried that with dictyostelium, and that turned out to be quite difficult. I mean, this is a fast-moving cell, and just getting enough frames in time turned out to be necessary to have a chance to get a good fit. But of course, there might also be issues with the model itself. So we were searching for something simpler. A cell which is geometrically simpler. What would you suggest? What is the most geometrically the most simple cell beyond keratocytes? I mean,
the thing that just moves without change.
But I understand it.
Keratocytes. So at least a persistent motion. Yeah. I think even simpler, beyond the spherical cell, yeah. So you should have some polarity, yeah. But right beyond something which is elliptic, or just a banger, yeah. A cylinder with round caps, so yeah. one of our former colleagues, Graham Letts, he came up with yeast. Yeah, it's not crawling, fair enough. Yeah, it's just growing. Yeah, digesting and growing. Yeah, it doesn't count as migration. No, it's a growth actually. Yeah.
But you can map it to it.
So we attempt to quantify, say, growth. Yeah, good. It's actually the monopolar growth that we're interested in. Yeah, so we have one of these quantities here, CDC42, which is sitting on one side, and which makes this yeast cell grow. Yeah. So we got these data, and then these data have been post-processed. The image data have been post-processed with TIL software to get data in the required format. And then we've got one species. I mentioned the CDC42, and this is then the coupling term that we are proposed. Then we propose to try to identify these two coefficients here. One is the threshold. So apparently one needs the CDC42 has to be beyond a certain threshold to initiate the growth. And then there's a certain growth rate here, this kappa 2. Yeah? The higher the K2, the stronger, the faster the growth. Yeah? So identifying these two parameters, that's what we did. So here in the top row are the data. Might be a focus issue anyway. So these are the computed solutions with the optimal solutions actually computed with this functional that I presented. So here's some solution for this other functional which I didn't present in detail, the smoother one. But the results are very similar anyway. Yeah, and that's what we got out then for the forcing strength for the K2 and for the threshold for the K1. Yeah, so we could quantify the individual cells. Yeah, and at least for the forcing strength, so this is pretty much in the right range that has been observed. So not for this test, but for other artificial data, we did also some. What did we do? Yeah, we tried to get an idea how significant these minima are. Yeah, so. So we haven't embedded it into any general framework like the Bayesian framework or something like that, but at least we assessed a bit how significant these numbers are. Not for this case, but for the other one. But in principle, that can be done. Yeah. Well, it's costly, of course, yeah, if you sample your parameter space. Yeah. Okay, so it's not much time left. So okay, let's come to the focal adhesions. This is a sketch here, essentially what's going on. We have seen some talks about focal adhesions. So roughly, very briefly, so we've got these patches which are adhering at the bottom of the moving cell to the extracellular matrix or whatever there is. And we've got these three parts of the membrane. So Freud and Lin, they looked at a model for this problem, and essentially it's a two-phase problem. Yeah, they have the adhering part and the free part. And they looked at the one-dimensional setting, and so you've got unknown. The unknown quantities are then the position between the adhering part and the free part, and the binder concentration, which they only consider in the bulk. So you assume it to be fixed here in the adhering part. It's a high concentration, it's fixed. And then you have this concentration subject to a diffusion equation here in the free part. And of course, for that this patch can grow. Look at the growth of that patch. For that it can grow, you have to supply binders, which is done here in this context by diffusion. Yeah, so that's their model. Yeah. Okay, so we embedded that into a phase field context, where the main notion behind that is, I mean, these patches, they have to be nucleated at the front of the cell, and they have to be disintegrated at the rear of the cell. So with respect to this two-phase problem on the membrane, you will have some topological changes. So it's natural. So the phase field method is a nice method that can deal with these types of problems. And so let's use that one. So this is one way of approximating this free boundary problem on the membrane. So I'm spending here a phase field function which serves to distinguish these two phases. So let's say it's 1 in the free phase, 0 in the other phase, and the adhering phase. Yeah. So there's some other quantities in here, but in principle this first equation describes the motion of the free boundary, and the second equation, yeah, this is our diffusion equation for the binder density. Yeah, and formally, as epsilon converges to 0, so there's some work that Dave O'Connor, my PhD student, has investigated. So formally, as you send the epsilon to 0, you recover a generalization, actually I should say, of this free boundary problem that I've presented before. Yeah, so formally at least. Yeah, so it might be possible to do that also in a rigorous setting, at least if the shape of the underlying membrane is known. If we now couple this to a geometric evolution for the membrane, that will be a very hard problem. Well, anyway, we did it. Computationally, we can still do that, of course. So couple it to a geometric equation for the membrane, where again we have some, be it a regularization term or be it some term that accounts for the elastic properties. And somehow I have to account for the adhesion. So I'm proposing here adhesion potential. To account for an adhesion potential, this is that corresponding adhesion term. So this adhesion potential is only effective in the adhering phase. It might look like this. So you have an optimal distance here that the membrane wants to have, optimal distance to the substrate. Yeah, in the free phase, this potentially is just repulsive. And actually also in the adhering phase, it's repulsive if you get too close. Trying to avoid here any invasions. Yeah? So this might happen in some contexts. So here we try to avoid that. Yeah? So this potential blows up as the distance to the substrate converges to 0. All right, so now given the progress of time, we did some tests where we compared with what Freund and Lind found with regards to the growth of some patches, which the growth is goes with the square root of the time. Yeah, so for some range we could recover this effect. So initially we've got some relaxation effects which has to do with using the specific method, this phase fit methodology. And later on we have a finite size effect. They have an infinite membrane, we have a finite vesicle. But here for a large region we can recover this growth type, that's fine. So this is, I think, is a more interesting case. So I'm seeding here two adhesion zones. One is here, one is there. So we call if this is a phase fit variable. If it's 0, we've got an adhesion zone. Here we have 2, where the binder density is high, relatively high. So this is then the shape of this object. You must think of having, this is basically a cross section from the top to the bottom through the cell. And the substrate is here at level 0, below the level 0. Yeah, so if you let that run, there's something else. So I'm supplying some binders here at the front, let's call it front of the cell here on the right, and I've got a sink term here on the left. I'm supplying binders on the right and I'm taking them away from the rear, however that happens, magically here. So could be by whatever transfer, if there's any transport, if they're disintegrated or switched off, however that works. Yeah. So this is what happens. So one patch here at the rear will indeed vanish, and you keep the other one which keeps on growing and even manage to shift the whole cell a bit to the right. Yeah. Of course, it's also becoming more roundish, which is due to the surface tension effect. So it might work better if you use the bending, the higher order surface equation. That might work better. Yeah, but in principle, we are able to. This is capable of describing at least the disintegration of these patches. Yeah, so nucleation still is an issue generally using this methodology. Okay, final example, tethering. Okay, this is just 2 slides and then I should stop. Yeah, we can, actually there's no surface PD involved here. It's just to do with this Wilmer flow, or Helfrich flow I should say. So we've got a constraint on the total area and a constraint on the closed volume, but it's in higher dimensions. It's also to show actually that it works in principle in higher dimensions. So we stretch a closed vesicle, which is formed of a biomembrane, by attaching 2 hard spheres and then using these adhesion potentials and just pull it apart. And if you don't do it in the right way, then this happens. So you must imagine here that there are these spheres to sit and I pull them apart. But then due to some numerical noise and some remeshing operations, I lose the contact to one of them. But if one does it in the right way, then one obtains something like that. Yeah, one of these tethers here form. Yeah. At the moment, it's not more than just a conjecture, apparently, regarding the typical size of these tethers. I was recently confirmed. So in principle, this could be of relevance, or this could be a basis for investigating philopods, as they occur at the front. They're also of relevance to the rear of the cell, but I think they're more important at the front of the cells, moving cells. Okay, so with that I want to stop. Very briefly, so we've used surface finite elements. They provide a mean to approximate geometric equations and surface PDEs and coupled systems, where the challenges arise from the degeneration due to moving vertices, degeneration of the mesh using the moving vertices. Yeah, but at least in only that can be controlled. So I never mentioned that, but these dimensionally reduced approaches to cell motility and all the other problems. I mean, of course, I'm losing quite a lot. I'm not considering at all what's going on within the cell. Could get away with boundary element methods, Green's functions approaches, etc., mapping everything to the boundary. Yeah, but of course, I'm losing quite a lot. The main advantage is this problem is reduced in the dimension. You essentially only have a two-dimensional problem or one-dimensional problem if you only consider a curve. So it's much cheaper to solve. Yeah, if you consider if you have fitting problems in mind, I want to make predictions, so it's much easier to get these solutions. Yeah? Much cheaper. Yeah. So and yeah, for some in some contexts that might be sufficient to do so for some objectives, for some goals. Yeah. Right, and then some preliminary work then concerns these focal adhesion zones and the formation of tethers. Okay, thanks for your attention.
Actually, I've seen that tether pulling in the lab, so I know how the signal should look like. And it looks quite a bit different than what you have in your simulation. It's basically a spherical object, and you pull out one very shallow or very thin tube, and there is a very localized crossover region. So what is different between an experiment with a fluid vesicle and what you did here?
You say there's something here in this region.
Well, the whole thing has a shape like
It should be more spherical.
yeah, it should be much more spherical.
Interesting. I mean, it's not fully relaxed, I should say. Yeah, so that might be an issue. The time scales. Yeah, so I'm just pulling apart. There's different time scales involved. There's a geometric equation, which essentially is a relaxation flow. So plus this additional forcing term, which comes from this adhesion potential from the adhesion. Yeah. So that could be a reason. This is not relaxed. Yeah. So, but if you change these time scales, you might get these types of shapes, much more rounded shapes here at the rear.
When you did your analysis for the mean curvature flow coupled with the surface PDE, were you always assuming that the mesh points were moving with the correct normal velocity?
Yeah, they move in normal direction.
You do the analysis where there's an arbitrary tangential velocity that comes in?
Provided you can control it. Yeah, it should be part of the scheme. So I suspect that there's a scheme here by the Fritz Alpha scheme, as they call it, a scheme that Hans Fritz and Charlie Elliott developed. So we have a tangential velocity, but which can be controlled. And you can show the convergence for that scheme following these lines of the proof of Gertjuk. It should be possible to couple that to the surface equation. I think it's possible. I haven't gone through the details, of course, I can't confirm that, but I expect that it is. Yeah, of course, that is beneficial. Yeah, the thing is, you get then this additional transport term in the surface equation. That's why I need to be able to control the tangential velocity. Yeah.
There are no more questions. We should go on. So let's thank the speaker again.